Have you ever stopped to think about your phone or your laptop? Really think about how we tell these incredible tools what to do. How do we get an idea from our head and turn it into an action on a screen? Well, it all comes down to language. And in this explainer, we're going to dive deep into the very beginning, the foundation of how we first learned to talk to computers.
So yeah, that's the big question, isn't it? How do we talk to a machine? On the surface, it seems pretty straightforward. We type on a keyboard, we tap a screen, we might even talk to a smart assistant. But what's really going on under the hood? How do you actually bridge that massive gap between the way we think and the way a machine, well, thinks?
And here's the root of the problem. Humans and computers just plain don't speak the same language. Not even close. A computer doesn't understand English or Spanish or any human language at all. You can't just tell it to make a cool video game and expect it to work. There's this huge communication wall right in the middle of it all.
I love this analogy because it just makes so much sense. Imagine you have a friend who can only understand two things, on and off, or yes and no. That's it. To have any kind of conversation, you'd either need some kind of translator or you'd have to learn their super simple but incredibly frustrating language. That is exactly the problem we've had to solve with computers. So how did we solve it? Well, over the decades, we've built these incredible translators. We call them programming languages, and they've evolved over time in what we call generations. These are the bridges that we've built piece by piece to cross that communication gap.
And here's the whole roadmap of that evolution. We started with the most raw, basic language possible, the language of the machine itself, and slowly worked our way up to the powerful, sophisticated languages we use today. But to really understand any of this, you've got to go back to the beginning. Back to square one, the first generation. All right, let's get right to the core of it all. We're going to look at the only language that every single computer on this planet understands right out of the box. No translation needed. Its native tongue.
And this is it, machine language. The key thing to get here is that this isn't just a language for computers, it is the language. It's what the processor itself speaks. Every single command is executed directly. There's nothing in between. It is the purest, most direct way you can possibly communicate with the hardware.
And this is what it looks like. Just a long, endless stream of ones and zeros. I know, it looks like total gibberish to us, but to the machine, it's the language of electricity. A 1 means a circuit has power. It's on. A 0 means it doesn't. It's off. To a processor, every unique combination of these signals is a perfectly clear command. Add these two numbers, store this piece of data, go find that information. It's crystal clear. This chart just lays out the situation perfectly. From the computer's perspective, machine language is a dream. It's lightning fast because there's zero translation. It's simple, it's direct, and it barely uses any memory. But for us, the humans, it's a total nightmare. It's incredibly slow and tedious to write. It's nearly impossible to read back. And trying to find a tiny mistake in thousands of ones and zeros, forget about it.
And all of this brings us to this term, low-level language. The level here is talking about the level of abstraction, how far away you are from the physical hardware. So a low-level language is one that's really close to the metal, so to speak. And machine language is the lowest you can possibly get. You're basically talking directly to the circuits. It's just so far from how our brains are wired to think.
Okay, so we've established it's really hard for us. But let's try to really put ourselves in the shoes of one of those pioneering programmers. What would it actually feel like to try and build something useful with nothing but ones and zeros?
This is such a great way to think about it. Imagine trying to explain a recipe for a cake to someone, but you're only allowed to use the words yes and no. Could you do it? Maybe? It would take an incredibly long and complicated series of questions and answers. It would be agonizing. That is exactly what early programmers were up against.
This whole thing can feel so abstract and technical, but it's important to remember it all started with people, which kind of begs the question, right? Who was the pioneer? Who was that very first person to look at a machine and figure out how to write down a complex set of instructions for it to actually follow?
And the answer is it's an amazing piece of history. The person considered to be the very first computer programmer was Lady Ada Lovelace, and she was doing this way back in the 1840s. She wrote what's now seen as the first algorithm for a machine called the analytical engine, a machine that only ever existed on paper. But what's really mind-blowing is that she saw that these machines could one day do more than just math. She imagined they could create art and music. She saw the future long before anyone else.
So obviously, we have come a very, very long way since the 1800s. We've got thousands of programming languages now that are so much easier to use, which might make you wonder, why does this ancient, difficult language even matter anymore? Well, let's talk about why it's still the absolute foundation of everything.
Okay, so let's boil it all down. What are the key things to remember? First, machine language is the only thing a computer's processor actually understands, period. Second, because of that, it's the foundation for everything else. Every single modern language, whether it's Python or C++ or JavaScript, has to get translated down into these ones and zeros eventually. Third, there's that big trade-off. Super fast for the computer, super hard for the human. And finally, and this is a big one, it's machine dependent. That means the machine code that runs on the chip in your laptop is totally different from the machine code that runs on the chip in your phone.
And that leaves us with one last kind of mind-bending thought. Every single app on your phone, every amazing video game with stunning graphics, all the software running our world, every last bit of it has to eventually become that simple stream of on and off. When you really stop and think about the fact that all of our incredible digital complexity is built on that simple binary foundation, what does that tell you? It's a pretty powerful reminder of just how far we've come and the fundamental limits we're always working with. Thanks for diving into this with me.